people said this experiment was impossible, so I tried it.
First in a series of videos about a chemical reaction discovered over 125 years ago. It releases
Thermite.
a tremendous amount of heat.
Oh no, the GoPro!
Liquefying metal.
It is so hot.
It is not an explosive,
They're creating lava.
but it can cause explosions.
That is crazy!
But the reactants are so inert, they can withstand a blowtorch indefinitely.
You think this whole thing's gonna blow up in my face?
In fact, when Hollywood directors wanted something that looked like a nuclear bomb, this is the reaction they chose. But in its most
Just PM close up.
common use, one basically unchanged in over a century, it has helped move billions of people all over the world. In the late 1800s, Carl and his younger brother Hans Goldschmidt were preparing to join the family business. Their father owned a chemical factory making dyes for fabrics, so they studied chemistry under Robert Bunsen of Bunsen burner fame. After their father's early death,
That's where it gets its name from, Bunsen.
Carl took over management of the company, later joined by his younger brother. One of Hans's first major research aims was to find a way to produce pure metals. These were essential for making dyes for everything from clothing and tablecloths to wallpaper. At that time, good dyes were hard to come by. Most were faint and faded further after use. Some required the collection of large quantities of exotic insects. These days, we take color for granted. But in this drab world, people would pay handsomely for bright, color-fast dyes. One such dye was Scheele's green, which was chemically copper arsenite. As its name suggests, it was toxic, though exactly how toxic is a matter of debate. Still, it became the dominant green dye by the end of the 19th century because its color was unbeatable. The red color of the British
So it's like only in recent years the colors actually developed.
Army officers' coats was made from cochineal, a Central American insect, mixed with tin. The addition of tin made the color darker and more intense, so the demand for pure metals was strong.
They had their experience in purifying metals by dissolving them in solutions or in acids and all kinds of things.
The incoming cyanide solution goes on dissolving the particles of gold left in the sand after amalgamation and liquefies it.
And then work with these salts, purify the salts, and then reduce these salts into their metal state. And every step that you would take would then again cause problems, right? Reducing it in a furnace, you have to deal with all the exhausts and the contamination through the carbon.
And metals are very difficult to separate from each other.
They form a mixed crystal, right? So
Like an alloy.
Like an alloy, right. They all become, in a sense, one substance that has
Alloy of what and what?
one melting point, which is why you have to kind of take some steps to separate them.
So Hans came up with a novel idea. He would react a metal oxide, like chromium oxide, with aluminum metal. And his hope was that the oxygen would swap partners, forming aluminum oxide and pure chromium.
Yeah, does it actually work?
This type of reaction is now known as an aluminothermic or thermite
I guess
reaction.
it does.
So I have come to visit Elektrothermit in Germany, a company that is a direct descendant of Goldschmidt's.
I feel like they've set this up like a tour of Willy Wonka's chocolate factory, but instead it's a thermite factory.
Here we are going to try to replicate Hans' first successful reaction. All experiments in this video were performed under the supervision of professionals taking proper safety precautions.
Originally, the first experiment was using chrome, but we're using copper, which is comparable.
This is like 300 grams.
Yeah, 300 grams of thermite.
Pour it in. All right.
We pour it into the crucible and ignite.
All right.
Now here comes.
That's it?
Yeah.
Ah!
Leave it.
Whoa!
It's like that one those firecrackers.
That is like fireworks. Wow, that's
Yeah,
impressive.
basically.
Where you bet he was surprised when he saw that.
So how much was that?
Handful of aluminum powder. And then you get this.
As you can see, the reaction releases a lot of energy. The temperature of thermite reactions typically exceeds 2000 degrees Celsius, and it can be as much as 2500. That's because aluminum forms very strong bonds with oxygen. When those bonds form, they release a lot of energy, way more than is required to break the copper oxide bonds we started with. This energy melts all the products of the reaction and makes them glowing hot. It is hard to express just how bright they
How
are.
do you get pure copper from this?
It feels like staring at the sun. If you see clips in this video where the highlights are overexposed, it's because it is so hard to judge how bright the reaction will be, and it's almost always brighter than you expect.
I mean, YouTube also compress this video and then
So that
compress by the editing also.
dropping down the bottom there, is that liquid copper?
That's liquid copper and basically the solution that was being created.
But if you get this hot mixture of pure metal and aluminum oxide, how do you separate the two materials to isolate the pure metal?
We're trying to set up an experiment that no one has ever seen before, and it's actually going to allow us to see inside the crucible.
We cut the crucible in half and we're attaching two pieces of thermally resistant glass, each 4 millimeters thick, as a window into the reaction. People said this would be impossible, that you wouldn't be able to see anything, or that the glass would just break.
We've never done this on camera. I'd really seen it this way, this clearly. And I think it's going to be fascinating to then start to analyze and make sense of this.
Now, this glass has been specially treated, so it shouldn't shatter immediately when it comes into contact with molten metal.
Wow, that is hot. That is really hot.
But the melting temperature of silica is around 1700 degrees Celsius, which is definitely lower than the temperature of the reaction. So the glass certainly will melt. The hope is it melts slowly enough to contain the reaction.
The glass will melt, and at the
They're
end
just hoping.
we have just a very thin layer of the glass at the end. So you will ignite it. It's up to you to place the igniter.
I think someone else should ignite it. I think someone else should ignite it.
Why?
Because I don't trust myself. We saw how incapable I was of igniting yesterday.
That's it?
Leave it.
For this reaction, we'll be using iron thermite, so a combination of iron
You
oxide
can just put the matchsticks in there. Come on now.
and aluminum metal.
Okay, it's good. Let's do this. Oh no, the GoPro. Oh boy.
Oh, GG's.
Oh no. Oh no.
Actually melting.
That's the end of the GoPro.
The reaction starts at the igniter and expands outwards in all directions.
To me, it almost looks like ants or mold or something. It looks organic in how it's sort of spreading. You see a pulse.
Yeah.
Boom, boom, boom.
It's living.
Yeah, that's what it looks like.
Yeah, this could be in one of the movie scene or something.
Why is there pulsing?
I don't know.
Okay.
We try to understand.
Huh?
We never knew that it did that. We do this for 100 years, and suddenly you find out, every portion that gets ignited does that.
Do you think that's gas escaping up? And that's almost what causes the pulsing? Like some gas heats up and then it shoots up and then it makes space for the next one?
Yeah.
That's what you seem to see over here.
Yeah.
Wow, that is hot. That is really hot.
I wanted to get a closer look, so I asked them to put some thermite on top of glass, and then I would shoot from below using this probe lens.
I'm ready.
Okay, we're rolling.
Another melting equipment. Nice.
It's rolling, it's rolling, it's rolling, it's rolling, it's rolling. There it goes, 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 there it goes. Wow! Wow! Yeah! The exposure is pretty good. Oh my goodness, incredible.
This is the closest I think anyone's ever filmed a thermite reaction.
Breaking. Okay, that.
You can see that the reaction proceeds in bursts. It reacts fast, but then pauses for a moment before advancing again.
And macro explosions.
Can I take it?
Sure. Yeah, take it, 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 take it. Oh boy.
I have two ideas about why this might be. First, thermite is a mixture of grains, big particles, of aluminum and iron oxide, and they need to be present in the right ratio to react efficiently. Maybe a little pocket reacts out to where the ratio is slightly less ideal until the heat builds up enough to trigger the reaction in the next pocket. My second idea is that in between the grains there is air. The reaction heats the air, which expands, increasing the pressure between the grains and possibly pushing some of the unreacted material away from the reaction front. So once that air escapes, the next patch can ignite. Once all the thermite has reacted,
So how does it react if it has no air inside the grain?
things get really violent. Molten metal is ejected out of the top of the crucible, and inside the liquid is sloshing around. This could be due to some of the materials boiling, actually turning from liquid into a gas. Now I know it sounds wild to think about metals boiling, but the boiling point of aluminum is around 2500 Celsius. Iron boils above 2800 Celsius, and there are other elements in the mixture like manganese that boil at just 2000 Celsius. Now once that boiling stops, the liquid settles down, and now comes the key to making pure metal. The density of liquid iron is more than twice that of liquid aluminum oxide. So iron settles to the bottom as aluminum oxide floats to the top.
Ah, yes.
Now, when the metal melts through the bottom of the crucible, the first liquid to pour out is iron. Only after it has drained does the aluminum oxide or slag follow. You can actually see the change from iron to aluminum oxide. Liquid iron has a viscosity like water, so you can see it coming out there and splashing. And then the slag starts right there. Yeah, it comes out smooth.
Really
cool.
Yeah.
Whoa.
And this is more like warm honey.
Yeah, you can totally see it.
Oh, very smooth.
Wow. It definitely gives you a sense of being right there, and you can see the flames coming off the front. And it still records. Look at the bubbles on the glass. You see those bubbles?
GoPro.
And the beautiful shot of the iron pouring out. I mean, this is impressive work for a camera that's on fire.
We're gonna put a cobblestone, normal street paver. Inside here it's made of limestone. We'll pour the thermite on top, then ignite it. Yes. And then we'll see that the cobblestone is less dense than that solution. It's gonna come up to the surface. Yes. Whoa. Okay. It looks like it's breaking into pieces. That's a good bit of lava. Did you see it? Oh yes.
Ordinary rocks like cobblestones rise to the surface, just like the slag, as the denser metal drops to the bottom. And this is key to producing high purity metal in the crucible. So Hans Goldschmidt had developed a process to make pure metals like chromium, copper, and iron. This could be great for chemistry and making dyes, but Hans suspected it could have even broader applications. He patented the process in 1895 and wrote it up for publication. He wrote, "The procedure that I have here is in its principles so extraordinarily simple that I could hardly have undertaken the time to present, if not for its surprising and extraordinary effects." Thermite was a solution looking for problems. One of the first applications of thermite was to weld metal parts in remote locations.
Wherever you need a very, very strong, very reliable weld in kind of a remote area where you don't have the luxury of bringing, tons of equipment and tons of welding gear, that is useful for thermite. Some of the first customers were, in fact, shipping companies. When some shaft would break in the middle of the ocean, at the time, you would be lost. And now having thermite to be able to at least fix that in some way that would get
They're going to fix it on the
home
way.
was actually very useful. It was being able to fix something or to fix cracks in engine blocks and to be super mobile with it. Because, like we said, it takes two guys in a bucket.
Of course, in this case, the iron thermite would actually not produce pure iron, but rather steel. This was done by including carbon and other alloying elements in the thermite powder.
Nobody needs pure iron. Pure iron is actually useless. It's very soft. It corrodes immediately, even in dry air. And nobody will want that, right?
You need iron with some carbon in it.
Exactly right. You need iron with some carbon. That makes it a steel.
So the majority of thermite produced today is steel thermite.
You have this steel mill that you can, move wherever you want it to have. After the end of the Cold War, we would use thermite basically to destroy, say, gun barrels from tanks. Basically, you have a portion of thermite that you basically stick into the gun barrel, and then you would ignite it. And then it would basically weld the gun barrel and destroy it, and it would be completely useless afterwards. Those are all kinds of weapons or stuff that were not useful anymore that we use thermite to destroy, because it's very quick and it's very safe.
And it's very final.
And it's very final. Once you've put that in, there's absolutely no way of making use of that weapon again.
A modern application of thermite is to
That was actually a genius.
use the heat generated to destroy information. Past a certain temperature, the Curie temperature, magnets lose their magnetism. So information stored on magnetic hard drives at high enough temperatures becomes unrecoverable.
This looks like a very different form of thermite.
Yes.
I'm used to seeing it as a powder.
Before it was also powder, and we dry it.
Can I pick it up or?
Yes.
It's not, it's like a normal piece of tile.
Yeah, lay it down.
Whoa! That's amazing!
200.
That is cool. So if we want to make sure no one can read the information on this hard drive, I could put this on top.
Yeah.
There you go.
When we
You
ignite
have to do the whole laptop, you can just take out the hard drive.
the crucible, we have this high temperature for a short moment. And here we have it for 10 minutes, so everything is destroyed.
So you're controlling the energy release to make it slower here.
Yes, the temperature is not so high, and the reaction is slower.
I am going to light this thermite tile in all four corners, and it's going to generate heat for about 10 minutes, and we'll see what it does to this laptop. All right, let's light it. Ooh, I like this. See how it's oozing? Whoa. It's a totally different effect. Whoa. Yeah, that's getting hot. It's getting to the laptop now. This is
Actually melting
really
the
cool. Like, you gotta see the molten goo coming out from underneath that laptop. That is wild. Whoa. After seeing so much thermite, this is a totally different version of it. Look at the puddle of metal there. Oh.
stabbing and then uppercut could use that. Come on now.
Yeah, nobody's getting any data off that laptop. That is awesome. I did not expect to see the logo in thermite.
Can I lift it? Of course.
I've never destroyed data like this before, but every time I get a spam call, I wish I could just magically make the... Given the amount of energy given off, that thermite could be used as an explosive. But it's actually not well suited for that purpose.
What makes thermite so interesting and so important is that you can control it so well. If you have an explosion, you can kind of calculate the energy really well and say it's, X amount of megajoules that you get out, but it's really hard to say over what time.
Maybe one of the reasons why this is not explosive is because when you have explosive reactions, typically your reactants are solid and the products are gases, which obviously expand a lot and create a lot of pressure. But in this case, both the reactants and products are solids or,
They're solids
or
and liquids.
Yeah.
Right. You have so much control over what's going on.
Woof. I feel like I got a sunburn from that.
This property makes it possible to take down structures where explosives would cause too much damage. In 1933, 4 weeks after Adolf Hitler became the Chancellor of Germany, the Reichstag building in Berlin was set on fire, and it would only be fully repaired 24 years later. But the burnt-out steel dome had lost its structural integrity and needed to be removed. Now, conventional explosives would have caused irreparable damage to the rest of the old building. So, on November 22nd, 1957, thermite charges were strapped to the dome, and when ignited, they melted through the steel, which fell neatly into the former plenary hall below, allowing the repairs to be completed.
Oh, that is nice.
Applications like this are possible because the thermite reaction can be carefully controlled. They have the ingredients so dialed in that you can actually ignite thermite indoors without fear of molten metal flying all over the place. This mixture includes some pieces of
That's kind of dangerous.
pure steel. They don't participate in the reaction, but they do absorb heat as they melt, so they help
So
control
they need this kind of
the
container.
rate of reaction and the temperature reached.
There you go. All right.
That's it.
That's it? I don't think it was in. Oh boy. Whoa. Wow. It's interesting, like looking at it through dark glasses, it looks like a cornbread muffin or something.
One of the really important parameters to control is how long after the reaction starts does the metal start flowing out the bottom of the crucible. This is known as the tap time. It's critical because if the tap time is too short, the metal inside doesn't fully separate from the slag. But if the tap time is too long, then the metal dissolves more silica from the walls of the crucible,
How to moderate that?
and it also comes out colder than it could have been.
So the chemistry of the steel actually changes over
The
over
longer
time.
it
Exactly.
stays in there.
The longer it stays in there, and this is why it's very important for us to be able to control how long it actually stays there.
You want the tap time to be somewhere in the middle, just right.
We've set up this experiment here to test, can we control the time when the steel comes out? So the idea is it should come out of this one first, then this one, then that one.
We're going to ignite all three simultaneously and see what happens.
You good? 3, 2, 1. Yes!
They all ignited at almost exactly the same time. But the tap time of the first crucible
We got one!
was by far the shortest.
Is it based on quantity?
2. It'd be amazing if this one stops and the third one goes. Like, that would be very, very impressive. Come on, third one. Wow! Wow, that's great. That's fantastic.
Another attribute that can be controlled is the temperature of the metal.
Here we have two different versions. So we have a version with 12% damping, and here we have with 25.
Sometimes you want the metal to come out a little hotter or a little colder.
There we go. Nicely controlled ignition. Well, that one goes a lot more. Whoa! You can see the 12% one went first. Whoa! You can see that, you know, this one starts first, so you can get a bit of a sense, but I feel like both of them reached 2000. I don't know.
The one on the right side is one of the less dampened portions, and the other one is one of the more dampened ones. We could dramatically change the temperatures in both directions, a little bit higher and significantly lower.
All of this control is achieved by carefully adjusting the thermite mixture.
This is the starting point of the making of thermite. About once or twice a day, a truck comes and drops in this. This is mill scale. So this is basically a mixture of different iron oxides. When you hot roll steel, the surface of the steel is very reactive because it's so hot and there is so much water involved to cool the rollers, so that the surface actually oxidizes very quickly and creates this mill scale. And then they use like water jets to blow it off the steel surface. And for the rolling mill, this is just a waste product, right?
Whoa.
There you go.
That is cool.
The mill scale from outside comes in here and then gets dried, because thermite and water, they're not exactly friends, and you want the mill scale to be as dry as possible and then stay dry. So this is how we dry it.
The iron oxide is shaken up the spiral ramp to the top floor, and there the particles are separated into different sizes and compositions before being mixed with aluminum powder.
This also has to be very dry, I imagine.
It's not as much a problem here because the way that it's being manufactured doesn't contain any water. With the iron oxide,
It's getting blown off with the water jets.
we have to control all the elements, the reactive elements, which is the iron
Looks like a cement.
oxide and the aluminum, to make sure that every portion has their very defined reactivity. And then we get the reaction that we want and also the chemical qualities in the steel that we want.
You guys use this word portion.
Portion, yeah, that's the way that we use. A portion is basically one bag of thermite.
No cameras.
Always breaking the rules, this guy.
So the portions are bagged up individually and stored in the warehouse.
This is our warehouse, but this is only one of them. And this is not even the biggest.
Can I ask you one question here? Okay, yesterday we saw there's a tremendous amount of energy in thermite. And in
But the whole thing blows up.
this warehouse, there's a tremendous amount of thermite. So the question for you is this in any way dangerous?
It's a fair question. There's
Can you smoke in there?
it's a fair
I don't
question.
think so.
They set up this demonstration for me to see how safe thermite is to handle. They want me to try to ignite this full crucible of thermite with increasing sized ignition sources. But I wasn't entirely confident this was a good idea.
Maybe you can help me ignite it?
Where's Christoph? Have you tried this, by the way?
No.
Well then, under these circumstances, I would get you some safety gear.
I'm to 95% sure that you cannot ignite it.
95?
There you go. That's
So
safety
it's a 1
gear,
in
dude.
20? Is
That's
that
safety
how
gear,
we're
dude.
doing it? This is a fireproof suit.
At least there will be footage how it happened.
So first, here's a little lighter. All right, let's give it a shot, see if I can get this to ignite. 3, 2, 1.
Definitely scared, but
I'm making some of the thermite particles here quite hot so that they are actually glowing orange. Oh, it's getting
Well-
quite bright. Are you getting worried watching that?
No, we're not going to
I heard you make a noise and I was like, no, he's getting worried. I shouldn't keep it on the same spot. So you think this whole thing's gonna blow up in my face?
No,
I hope not. So you can see, like, even getting it
glowing hot.
glowing hot, it still won't ignite. All right, let's pull out a bigger torch. I'm gonna try with this one. Got a nice big blue flame there. I feel like this is not as hot as the other lighter. So I'm getting a little bit of orange there, but just barely. We're gonna have to bring out the big
Yeah,
gun.
it's gonna blow up anytime.
All right, let's torch it. In 3, 2, 1. Do you think we can build up enough heat? How hot? 500. Is he saying 500?
Yeah.
I can see a lot of thermite glowing orange. There's some pieces coming out.
Nice and glowing.
700 degrees. But I think this is an excellent demonstration that thermite is not going to ignite under normal conditions. Wow.
There you go, it's still glowing.
Did it melt?
Yeah, that can happen.
It can melt and not
ignite.
Not ignite. What the? That is
This is the
absolutely
bank on
nuts.
thermite.
Obviously, there is a lot of potential energy here, but getting that energy is really, really difficult. So if it would catch a fire and, you know, whatever, the wooden pallets would burn, you would not be able to ignite the thermite.
Would not even.
No, it would just sit there and it would just ignore you.
The key to this lack of reactivity is the aluminum powder.
The aluminum is quite stable because it's covered in aluminum oxide.
Just light up the aluminum there.
And only if it gets so violently heated that that layer breaks down in a large number of particles, then the reaction can start.
So the aluminum oxide is like the secret stopper of thermite.
Exactly, the seal.
This reaction has a very high activation energy, so it can't be started by a lighter or a propane torch.
Okay.
This is why we've been using barium hydroxide igniters, basically the same stuff that's in sparklers.
Happy New Year!
It gets hot enough to break through the aluminum oxide layer and start the reaction.
We want to make sure that the ignition temperature is so high that you can only light it deliberately. Because once it's going,
I'm gonna push the button. In 3, 2.
there is no way of stopping it.
That is crazy!
I was filming in Germany for a full 5 days, so this is just a taste of what's to come. We'll find out how thermite reacts with its environment, and we'll have a dedicated video on the most common application of thermite: welding railroad tracks together.
There probably will be millions of people watching this video. Most of them have probably ridden on a train. What is the likelihood that they have ridden over one of your thermite welds?
Let's part of this video. That's nice.
They will.
100%.
100%.
So make sure you're subscribed to
Get
be
over the link
notified
there.
about these videos
Okay.
when they come out.